Hello, students. We've learned now that heat is one form of energy, and typically heat flows from a higher temperature to a lower temperature in substances. We've also learned that heat is measured in the units of joules and calories as well. So in this particular video, we're going to discuss how the amount of heat absorbed depends on what is referred to as the specific heat or the heat capacity of a system. We see this a lot, for example, in boiling things like water. So when you heat a substance, its temperature changes. And we're going to use the variable Q for heat. So one of the first things we need to know is that when I heat something, there's a temperature change. And how do I denote temperature change? Typically, we use what's referred to as a delta for a change. So delta T equals the final temperature minus the initial temperature. So that difference is the temperature change, okay? So whenever there's a delta, it's final minus initial. And if it's delta T, it's final temperature minus initial temperature. That shows the temperature change. So if there is an increase in temperature, right? So if the temperature change increases, right? If the final temperature is higher, right, than the lower temperature, let's say I'm boiling water, that's a positive delta T, or you can think of as delta T goes up, and that is directly proportional, okay? It's directly proportional to the amount of heat that you have to put into the water to raise its temperature. So when I boil water, I put heat into it and the temperature goes up. So I notice that the delta T is going to be positive and the heat is going to be positive because it's gaining heat. The water is gaining heat, so its temperature goes up. Let's say from, I'll use the example, it started at 25 and now it goes up to 26. But how do I make this direct proportionality an equation that's useful into something that's equal? I need what's referred to as a proportionality constant. So what's the proportionality constant? Heat capacity. Heat capacity is the amount of heat needed to raise the temperature of some substance or tool or item by 1 degree Celsius. So how many joules or how many calories does it take to raise this object, right? So let's say like a bomb calorimeter, 1 degrees in Celsius. And that heat capacity is written as C for capacity. So we get Q equals cat. So you can think of, it's the same concept as, I know that circumference is directly proportional to, let's say, the diameter of a circle, right? So the circumference, the length around the circle is proportional to the diameter. As the diameter goes up, so does the circumference. Well, how do I make this direct proportionality equal? I need a proportionality constant. And what's that constant? Pi. So it's the same concept with, okay, if temperature rises, so does Q. It's directly proportional. I need a proportionality constant. Oh, what's the constant? The heat capacity of the substance that you're heating. Now in chemistry, a lot of times we're going to use, right, different amounts, different masses. So when the amount of change depends on the substance and the mass, we use what's called specific heat. So this is a similar concept to the heat capacity. It's the quantity of heat needed to raise the temperature 1 degree Celsius, but we just add a unit of mass, right? So it makes sense. If I have 1 gram of water versus 2 grams, the 2 grams is going to require twice as much energy to heat the water up 1 degree Celsius. So we refer to that as specific heat. Some books even call it a specific heat capacity. I don't like that because students get confused between regular heat capacity and specific heat capacity. But for the most part, whenever you hear specific, you're hearing that it's dependent on the mass. That's typically what we use in chem. So instead of Q equals cat, It's Q equals MCAT. And people are familiar with the MCAT, you know, the entrance exam to medical school. So that's how I tell students to remember. Q equals MCAT. M stands for mass, the C in the cat, and I put a little SP, you're not going to see that, but is specific heat and delta T. Sometimes I write specific heat as SH. I don't like that because then that's well, I don't need to say that. I like MCAT better. So what are some examples of specific heat? So the unit of specific heat is the energy, right? The amount of energy, right, that it takes to raise 1 gram of a substance 1 degree Celsius. So I use the concept of, you know, if I had 1 gram of water to go from 25 degrees Celsius to 26 degrees Celsius, right? How much heat would that require? And I told you earlier it was 4.184, right? So the specific heat for water in units of joules is the specific heat of water is 4.184 joules per gram degrees Celsius. So if I have 1 gram of water and I want to raise it 1 degree Celsius, it requires 4.184 joules. Why? Because that's a specific heat of water. That's equal to 1 calorie per gram degree Celsius. Why? Well, because that is a nice clean reference point, and that's what they use as an equivalent form of energy. 1 calorie is 4.184 joules. Now, the one thing I want you to notice is water has a really high specific heat. If you look at all these other substances, they're much lower, right? When I boil water in a pan, the metal gets hot faster. Why? Well, it has a lower specific heat, right? So if you look at aluminum, look how low the specific heat. So it gets hot first before the water does. So water has an extremely high specific heat. You can think of a specific heat as the resistance to change temperature, or the resistance at who's better at maintaining temperature. So water has a really high specific heat. That's why coastally, the temperature doesn't deviate that much, right? Coastal Southern California, 72 degrees. Why does it stay that way? We got a huge body, the Pacific Ocean, that helps maintain temperature. It doesn't lose heat very easily or gain heat, so it maintains temperature. Unlike the deserts, which doesn't have a lot of water vapor in the air, you can have extremely high temperatures in the day and it's really cold at night. Okay. So again, energy, specific heat capacity. So if we look at this, Q equals MCAT. So can I apply this to solving word problems? I can. So what is the specific heat of a metal? Again, I don't want you to memorize all the specific heats. That's pointless. You'll have a table and you'll be provided those specific heats unless you're asked to calculate that. The only specific heat I want you to know is that of water. What is the specific heat of a metal if 24.8 grams absorbs 65.7 calories of energy and the temperature rises from 20.2 to 24.5 degrees Celsius? So remember, Q equals MCAT. So you can directly plug everything into this equation and then solve for the C, or you can rearrange it. And how can I rearrange it? Divide both sides by mass and delta T, and I get the specific heat is going to equal Q divided by the mass delta T. And that's what I need right here. So I know delta T, why? This is my final, because this is what I heated it to, 24.5. This is my initial. So when I do the subtraction, I'm going to the least precision or placement value, which is the tenths. So delta T is 4.3 degrees Celsius. So now that I have my delta T, I can plug everything in. Heat, the specific heat, is calories per gram degree Celsius. They tell me it requires 65.7 calories. I plug in the mass and I plug in the delta T and I get the specific heat for that particular unknown metal. And I see that it's much lower than that of water. Water specific heat is 1 calorie per gram degree Celsius. And again, the reason why water has such a high specific heat, it has more modes of absorption, right? It can absorb heat and it can change into translational motion where it goes in one direction, right? It can go into what's called rotational motion where the water molecules can rotate, right? It can go to vibrational absorption of energy where you can think of the bonds in the H2O as springs, and these springs can move back and forth or in and out of the plane. So it has all these modes of absorption to absorb that heat transfer and not change its temperature. If I think of a metal, it's in a fixed lattice structure, right? It's in a fixed structure. All the metal atoms are right next to each other and they can't move because they're in a solid state. So all they can do is vibrate and oscillate. So they get to vibrate and vibrate really rapidly, and all of a sudden it gets really hot really fast. Can we do a calculation? Well, how many kilojoules are needed to raise the temperature of 325 grams of water from 15 degrees Celsius to 77? So again, what do we need? Q equals MCAT, right? Do I have M? Yep, here's my mass. Can I figure out delta T? Sure, here's my T final, here's my T initial. So the one specific heat I do ask you to know is that of water, and this is water. Now, they want to know how many kilojoules of energy. So the energy, remember, is joules, and that's your heat. So once we get the joules, we can convert it to kilojoules using the metric system. So how am I going to do that? Well, I can just plug everything in. Q equals what? 325 grams. My specific heat, I know for water, it's 1 calorie per gram degree Celsius, but it's also 4.184 joules per gram degree Celsius. And then my temperature difference, 77.0 minus 15.0. So my delta T, that value, because I'm following the rules of addition and subtraction, should end in the tenths. So that's what I get here. My Q equals the mass, right? Times I put the delta T here, right here, but it's a 62 degrees Celsius, and we see that to the tenths. Here's the specific heat of water, which is that. But now we use a conversion factor method because I wanted kilojoules, and I say, well, in 1,000 joules, right, there's 1 kilojoule. So the unit of joules cancel, the unit of grams cancel, the units of degrees Celsius cancel, and I'm left with kilojoules. And I get 84.3 kilojoules is required to raise the temperature of 325 grams of water from 15 degrees Celsius to 77. So I hope that helps. Thanks for tuning in, and I appreciate you guys watching.